Hi, Matt 2504. So here is project number 2. Let me say ahead of time, it seems to me like there is a lot of stuff on this project, formulas and code and descriptions and all kinds of terms. Don't let that intimidate you. We give all these formulas and background and description to actually make things easier. So here's what this project is about. So first of all, this is work in pairs. That's obvious. The submission is similar to the project one style. Just please make sure that you get the full 10 points for GitHub repo, hand in, name things exactly as we ask to make things easy for us, and then follow instructions exactly. Have a git ignore. In this project, please put your code also, except for the scripts, in a module statement. That's not difficult. Claire can help you with that. And have a simulation script that is the thing that actually runs and creates the output. So you're creating a discrete event simulation engine. Now, there's also a tag-along task, which is the perspective seminar by incredible Dr. Mehta Mehta. So Mathili, you can also call her Mehta. And just follow that seminar as you did in the start of the course. All right. Now, here we go, and we describe this model that you're going to simulate. It's a stochastic model, i.e. a random model. It's called a modulated open Jackson network. So a Jackson network is kind of a well-known model. It's a model of queues, of many queues, a network of queues, of items that moves between the queues. Open just means that items come from the outside and also leave the network. So it's not closed. And modulated, that's this kind of slightly different thing that we're doing in this project. The parameters or the speed at which jobs work or servers work and give service is modulated. And in this case, it goes between slow and fast, slow and fast, slow and fast. Okay, so open Jackson networks are well known. Modulated ones, not really. That's what the project is about. And what we have here is an overview and a description of this model. So basically, you have stations. A station has a server and a waiting buffer. You can think of it as a very kind of rough application of this project. Think of an amusement park, such as Dreamworld, down there between Brisbane and the Gold Coast. Okay. And a server or a station is a ride, and customers or jobs or items, in this case people, move between the rides, and when they get to a ride, they queue up and they queue, and then they get their service, so they have the ride, and then they move to a different ride. Okay, so the number of servers is fixed. Maybe it's at 5 or maybe it's at 100, etc. And you could think of this model as customers or jobs. They can be numbered with this little l, and that can go on to infinity. So they come and they go and they come and they go. And they can be either out of the system, they still haven't arrived, they don't exist, or they can be in a system in a buffer. That means they're queued for a ride. Or they can be in a station and they're actually having the ride, they're getting the service, or they've left. Okay, so jobs are like that. Now, you don't actually need to code for individual jobs. That's this warning. So all you're going to do in terms of the system state is only think of the number of servers that you have, and in each one you have an integer which describes a positive and non-negative integer, which describes how many jobs are in that server. Okay, so this is a continuous time system, and you're going to do discrete event simulation. You'll learn about discrete event simulation in the lectures shortly. You could start this project way before you understand discrete event simulation, because you want to understand it first, and the first task has nothing to do with discrete event simulation. Neither does the second. So each station has a parameter mu, a positive parameter, which we call the service rate. So the faster mu is, the faster the station is. If you take the inverse of mu, the reciprocal of it, that's the mean service time, though how long does a ride take, okay? Is it a long ride, short ride, or long ride? When a job arrives to station I, if nobody's in the queue in that station, then service immediately begins. However, if a job arrives to station I and somebody's receiving service, then the job queues up. There might be others in the queue, okay? So it's as though you arrive to the ride and, you're ready to go on it directly, or you arrive to the ride and you need to queue up. Now, the rate of arrivals from the outside world is alpha. And you could think of it, even though in an amusement park you enter through the main gate, here you can think of it, you arrive from the outside world and you go to some arbitrary server or ride I. So alpha I can be 0. That means there's no arrivals from the outside world, but we must have alpha I positive for at least 1. Okay. So the mean time between arrivals from the outside world is again the inverse of alpha. Okay, alpha I to the -1. And what we have here is also modulation. So we'll see about modulation in a second. Now, how do jobs move between stations, between rides, between servers? So when you complete service, what you do is you go to this matrix P, and the matrix P has a row. And if you complete service at, say, server 7, then you go to row number 7, and you go to the next ride according to the probabilities on that row. Now, the sum of the probabilities in the row does not have to sum to 1. It can be a bit less than 1 because you've got this probability of actually then leaving, right? So you call that mathematically a substochastic matrix. Okay, so it's not like a matrix of a Markov chain, if you know what that is. It's a matrix of a Markov chain not. Well, that the sum of the row can be less than 1 because if you don't go anywhere there, then you leave to the outside world. Okay, you can return to question 14 in big homework where you use a sample function for stats base to kind of see where you're going. But the point is you kind of think of it as you finished a ride in an amusement park, you just got out, you just received service, you being a customer or a job in this case. Where do you go? Well, there's this matrix P, and you just choose where to go randomly according to that matrix. Perhaps behavior in an amusement park is kind of like that. Now, here's a modulation component. So we don't just have service rates, mu1 up to mu(l), but we have two sets of service rates, the superscript 1 and the superscript 2. And let's assume that the superscript 2s are always faster across all servers. Okay, so this is not the most general modulation. It's just kind of, you've got your slower rates and your faster rates. And what modulation does is we move between being in the slow mode and the fast mode, the slow mode and the fast mode. And that change doesn't happen so fast generally, but it happens. Okay. So we move between slow and fast. Now, how does that change happen? So independently of everything else, you've got two other rates. You've got gamma 1, which is the rate of going from slow to fast, and you've got gamma 2, which is a rate of going from fast to slow. And the inverses of these are the mean time in being fast and slow. So it's kind of like, imagine in an amusement park, somebody on the side kind of says, hey, now service will be faster. How is service faster? Maybe by putting more personnel on the rides or maybe shortening the ride time. Okay, and then service will be slower, and then it'll be faster, and then it'll be slow. So this modulation happens. Now, there's just a few interesting quantities associated with that. So one is this R superscript 1, which is like this. This actually happens to be the long-term average proportion of time where the system is in slow mode. Okay, you can see it. So you can use either this form or this form. This form is easier to kind of look at, but this one is actually, you can see the mean time of slow in comparison to the mean time of slow and fast. That kind of makes sense. So 1 minus that is R2. So, the sum of R superscript 1 and R superscript 2 is 1, and so the system is in long-term proportion, slow and fast. Now, if we had the parameters in a way such that R1 was 1, so the system was just slow, or R2 was 1, the system was just always fast, or maybe not just 1, but close to 1, okay, in both cases, then we actually have, and you can get these cases by actually sending gamma 1 to be 0. So gamma 1 to be 0 means or very close to 0, like 10 to the minus 8 or something like that, means you hardly ever leave slow mode. Or if gamma 2 leaves 0, you hardly ever leave fast mode. So the system is stuck in either one of two modes. Okay? So then you actually have two interesting test cases, because in these cases, what you have is that the system is not a modulated Jackson network. It's just a Jackson network, right? So you will use these test cases for testing the system, because for Jackson networks, there are explicit results. For modulated Jackson networks, we don't really have explicit results. Okay, and that's why you're doing the simulation. Now, just a little note here. When the system changes from slow to fast and a job is in service, and that might happen, right? Then you draw immediately the next time for the service duration to end. This is explained in great detail here. Now, with all our assumptions that service times are exponential, this actually makes a lot of sense. The system is memoryless, etc. But that's a stochastic process thing. Unless you're doing stat 3004, did it last semester, don't worry about this too much. But this is important for your implementation, this description here. So just another statement, in a modeling setting, you would probably want modulation to occur at a much slower rate than service and arrivals, right? So jobs move through the system, and from time to time it modulates and change. But there is a case, if you let gamma 1 go to infinity and gamma 2 go to infinity, and maybe you let them go to infinity in some way that there's a proportion between the two, or you just equate them and let them go to infinity, then the system will actually just act like an open Jackson network, because it's going to modulate very quickly between slow, fast, slow, fast, slow, fast, slow, fast, slow, fast, slow, fast, etc. And the actual rate, service rate of job I, is just going to be this convex combination or weighted combination of the two rates. Okay. So you call this case a super fast modulation. Again, when we say something going to infinity, what I mean here is not you're going to simulate this thing going to infinity. You just choose parameters such that these things are quite high, okay, in comparison to everything else. Okay, and these average service rates, mu tilde, are also important. Ooh, so as you see, that's a bit of a thing to digest. You need to read it, think about it, watch this video, and think about it more, discuss a bit, and then understand. Okay, so just an overview of the model parameters. So you've got L, that's the number of servers or stations in the network. It's also the number of queues. So then you've got external arrival rates. They can be 0, some of them. One of them has to be positive. You can put them in a vector alpha. You've got the slow service rates, okay? And they all have to be strictly positive. You got the fast service rates, and I didn't say here, but mu2 is mu superscript 2 is greater than mu superscript 1 for all subscripts. And you've got the modulation rates, it's gamma 1 and gamma 2, and you've got the L by L routing matrix. That's actually how the network is structured. But just to make things a bit simpler, what we'll do is we'll do mu I2 just to be some kappa times mu I1. So kappa is greater than 1, and we call kappa the speed up, right? So if kappa is 2, it means that the fast rate is twice as fast in comparison to the slow rate. So when we do this, then we don't have to use these superscripts 1 and 2. We'll just call mu superscript 1 mu I, and mu superscript 2, which was not going to be a parameter, it's going to depend on kappa, is going to be kappa times mu superscript I. So then the parameters of the network, and these are the ones that you're going to use for the project, are just as before, except that you don't have your mu1s and mu2s. You just have mu's, and you've got a kappa. So kappa says how much the system speeds up. So just note that when you do this kappa, then you also have the speed up rate, and this is now the vector mu tilde is the vector mu multiplied by this scalar. You can work out this calculation and see that I didn't mess it up. Please let me know if I did, but I think it should be okay. Okay. So gamma 1 times kappa plus gamma 2 divided by gamma 1 plus gamma 2. So one more thing is, instead of parameterizing the system with gamma 1 and gamma 2, we might want to parameterize it with gamma 1 and R1. Okay, why? Because gamma 1 is kind of the rate of modulation. It can be high or low fast modulation, and R1 is the proportion of uh, of time that we are in slow state. Okay, so you might do that instead of gamma 1, gamma 2. In this case, you kind of specify these numbers and you read gamma 2 to be gamma 1 times R1 divided by 1 minus R1. You can just solve for it from the equations above. Okay. Just another tip. Since all random variables are exponential, just be aware this is how you can generate an exponential random variable. Set, for example, dist is exponential mu. And then you would do rand of dist, it gives you an exponential. So here, for example, we get 1,000,000 of these and then do the sample mean of them. Okay. The inverse of the sample mean is going to be, again, the rate of, it's going to be 0.4. And the 1 over the mean here is also going to be 0.4. Only now I see, and let me fix this. What I see is in Julia, in the distributions package, the exponential gets not a rate, but gets a mean. Okay, so we gave a mean of 2.5, and right, so I'm gonna put here 1 over mu, and this will be okay. All right, so the exponential gets the mean, meaning the inverse of the rate, not the mean, it's not the rate. Okay, so this is going to be fixed, but I'm not going to change the video. Okay, just a bit more. Now, when you get to such a network, you can you have something called the traffic equations for the network. And we actually give you code for these traffic equations. So you want to understand the traffic equations, but you don't really have to program anything associated with these traffic equations. So what are traffic equations? Traffic equations, they just say, what is the flow rate of jobs in a queue or in a server or in a station? Queue, server, station, treat them as the same thing, okay? Or in a ride, in the amusement park setting. What is the flow of jobs through that? The rate of flow, meaning jobs per unit time that flow through that. Okay. Assuming everything is stable, assuming that there's not too many jobs and the network kind of blows up. And what you get is you get this matrix equation. The unknown here is lambda. Okay. You can pretty much look, this equation is exactly this. What it says is that the rate lambda I flowing through a station is the outside rate coming alpha I plus all of the rates coming from the inside, from other jobs. So that's summation of j. Now we're summing over j here, j to I. Okay, so we're taking the column of the matrix P. That's why you have here a P transpose. So I'm just recording. So, sorry, is that all right?
Yeah. I'll come back later once you finish.
Sorry. Okay. Okay. Sorry for the disturbance. Okay, I'll just continue if you don't mind. Okay, so observe that lambda I is, yeah, so that's it. All right. Now, if lambda I is less than the effective service rate in all cases, then the network is stable. And in this project, all you want to do is simulate stable networks. So you don't want to simulate networks where you have too many arrivals from the outside and not enough service rate, and queues just grow and grow and grow and grow. So the queues are going to be stable. Now, it doesn't mean that the queues are at 0, because there are these random fluctuations in the system, because service times and inter-arrival times are random. So how do we quantify the stability? Well, we can call rho I, that's the load of a server. That's going to be the rate of arrival divided by the effective service rate, this mu tilde. Again, effective service rate, mu tilde modulates between, captures the modulation between slow and fast. Okay. And if all these rho i's are less than 1, then all queues are stable and the network is stable. And specifically call rho star the maximum of all these rows. And that's actually going to be the kind of the bottleneck load. That's going to be the load on the station that's actually busiest, maybe the most popular ride, perhaps in an amusement park setting. Okay, so we are going to vary this rho star, and as a function of that, see the load in the system. So let me just show you this, and we actually give you code for this. So in the background, we have known queuing theory results and overviews of question to investigate. So a quantity from queuing theory that you don't need to understand the derivation of, but you can just take it as given. So to understand the derivation of, you need to do something like in stat 3004, continuous time Markov chains, and do a bit more with that. Okay. So this is rho divided by 1 minus rho. That's kind of a very fundamental kind of expression in queuing theory, etc. And this is when you increase the load on kind of a single queue, what you get is this is a plot of rho divided by 1 minus rho. Okay, so rho goes, as rho goes closer to 1, this thing goes off to infinity quite quickly. So that's actually the mean number of jobs in steady state when the system runs for a long while and you do a long time average of that, okay, of how much congestion there is. Lower rho, little congestion, higher rho, much higher congestion. That's kind of a fundamental thing in the theory of queues. Okay. Now, it turns out that if our system is with the exponential processing times and interarrival times as we have, and if there's no modulation, then each of the individual queues in a Jackson network also has this. So if you were wanting to see all queues together, you would just do superpositions of these curves. Okay. So that's something we can compare against. All right. And we'll get to that because in your second task, what you want to do is you want to make such curves for these example scenarios. So what are example scenarios? Well, we're actually giving you the struct network parameters, okay, which actually models the network. So again, number of stations, the vector of arrival rates, the vector of service rates, the routing matrix, and the gamma 1 rate of transition from slow to fast, gamma 2 rate of transition from fast to slow, and kappa is a speed up parameter, which says how much faster is a faster in comparison to the slower. We're using these packages, parameters, and accessors that gives you this keyword arguments that basically gives you an easy way to construct such a struct. You'll see this in a second. And there's also a function average service rate, that's this tilde mu. Okay, so this thing, we're just giving you this, it's exactly this thing. Okay, so that's kind of for computing this mu tilde. That's just a helper one-line function. And we're giving you 4 scenarios to work with. So scenario 1, scenario 2, scenario 3, and scenario 4. Okay, so please work with these 4 scenarios. Each of these is of type network parameters. Here, by the way, you see how what you get with this act with key KW, keyword arguments, this macro just modifies the structure to have kind of a constructor with keyword arguments where you can name what L is, what alpha is, what mu is, etc. Okay, and it also allows you to have default values. Hence, if we don't name those, we get the default values. Okay, now what you get with this accessors packages, you get this at set macro, and that's important for modifying a scenario and making a copy of it. Remember, structs in Julia are immutable unless you would have said mutable struct, right? So this thing actually creates a copy of scenario 1 where you modify P to be different. So scenario 2 is just like scenario 1, but P is different. And scenario 3, slightly different. And scenario 4 is kind of a big scenario where things go everywhere. You got 100 and there's all kinds of, so we don't see what the P is. But in these cases, this P is like a ring network, because look, you can go from Q1 to Q2 with probability 0.8, or with probability 0.2, you leave. So you're kind of circulating around every time with 20% leaving, okay? And etc. for the other ones. Well, they're different. Okay. So in task one, you'll just think about the modeling assumptions. You'll digest everything we spoke about here. You'll probably read it once or twice. You'll understand this network. You can do this right now. You can do this task right now. You could, I mean, meaning you don't need anything from Claire's lectures for this task per se. What you can do is you can also listen to Anna Foglin's YouTube talk. That's a prospective seminar speaker that spoke in previous years. So she's actually a simulation professional. So she creates simulations like this for things like, say, the amusement park and tries to make them realistic. What you want to do in this task is actually say, why is this model somewhat realistic for the amusement park, but why is it also not? Okay, that's what you do in task one. So that's just a write-up task, but when you finish this task, you would have understood the terminology well. Now, task two is a task of doing computation for Jackson networks, but it's not simulation, not simulating anything, no random variables, no real code that you're going to create, just some scripting. And what you're going to do with this task is you're going to actually create parameters here. So these parameters don't speak about row, about the load. They're not going to speak about row star nor about row. So we give you this extra code, which does the following. Let me explain. So the maximal alpha scaling function gets a network, and it tells you how, for that given network, how much you can increase the arrival rate with keeping the network stable, right? So for example, if you would take this network, take scenario one, right? If I would increase the arrival rate, increase from 0.5 to 0.7 to 1.2 to 1.3 to 1.9 to 2, etc. At some point, this network will break, and one of the queues, because our mu's are just 1, 1, 1, okay, and because of the way the routing is, one of the queues would break, or maybe more than one, and the network would become unstable. So this function tells you how much we can do such a scaling. And then we use it in this more important function, and you're going to use this more important function, set scenario. You're not going to use this maximal alpha scaling, okay, unless you want to for some reason. This function, you give it a network. You give it the row star that you want for that network. So you say, I want row star 0.99. I want row star 0.8. So you want to say what's the bottleneck queue in that network. And you can also modify the kappa and you can also modify the gammas, but it comes with default parameters. And what this function is doing is it's going to scale the alpha vector by the maximal scaling times this row star to give you the network with that given row star. Okay, so if you apply set scenario to these guys, each of those scenarios, but with a given row star, and also with given other parameters that you would like, you're going to get as a return some parameters of a slightly different network, and that network is going to be exactly that row star. So what you're asked to do in this task is just use this after you understand it. Okay, use it on the 4 scenarios in the 3 test cases. So set parameters that approximate. The approximate is an important thing here. The always slow case, the always fast case, or the super fast modulation case. Okay? And in all these cases, you're going to get curves of, you can then plot curves of rho I divided by 1 minus rho I and do a superposition of these curves. So plot curves, just 4, right? Well, 12. But they're going to be the same. So just 4, just 4 for each scenario. Plot curves like this and have that code ready for the mean steady state of the whole network. It's not going to be for individual queue, for the whole network. Okay. The reason you're doing this is, first of all, just to understand how to work with these kind of set scenario things. Okay. we've done the computation with the kind of linear algebra here. This is a backslash operator of linear algebra. We solve the traffic equations here, and we get lambda, and then we kind of compute what is the best lambda the alpha that you can get. So we have done this for you, but you're going to now have this code here, and you're going to use it as test code of your actual simulation engine for the case of no modulation. And again, the always slow, always fast, and super fast modulation is like no modulation. So your system will have modulation in it, but it's going to do modulation and think like it's no modulation. So if there's trouble there, then there's probably trouble with your simulation code. Then you get to task 3, and this is really the heart. This is where you're actually going to code some stuff. This is where you're going to build stuff. This is the simulation engine based on Q states. Okay, so this simulation engine, we wanted to have an interface of two different functions. So the simnet trace function and the simnet estimation. Let me explain. So, and here inside, you're going to put all the good stuff, right? So you're going to call the simulation. But we do ask you to avoid code duplication. So the code you will call from here and to here, and that code means other functions, which are probably in other files and other modules, etc. So that code should be reuse code. So you don't duplicate the code that's here and here, but this is what you're doing inside. Okay. So simnet trace is you get a network and you run it for a time. See, the default time is not too long, like 100. And you just plot a return, some data structure, which kind of has all the queues over time and also the fast slow. So you could potentially plot this return value. So we don't specify exactly what the return value is, but it's kind of like a complete trace. It's like a plot of the whole network, right? You might not use this for scenario 4 because scenario 4, has like 100 queues, but if you do it for scenario 1, then you've got 3 queues. Okay, and it's a return value, and you kind of see their trace. Simnet estimation, see, by default, you'd run it for a simulation time, which is longer, and you'd also do a warm-up time. You'll understand what that is in the lectures, but it's basically only to start collecting statistics after a warm-up, all right? And here, what you're going to do is just return kind of just return a single number, the estimated total mean queue length. Okay, so you're running this big simulation, it's running for a long time, and it's just returning you the estimated mean queue length. Okay, so what you're asked to do in this task is to code this up, and you're also asked to do some plots just of simnet trace and see that simnet estimation works. From this point on, you won't touch simnet trace, but it's good to have for debug, for understanding. So you want to see for short runs what's happening. Simnet estimation you're going to use in the remaining tasks. Now, let me just say that if I'll go here quickly to the course, while in contrast to project 1, where we gave you code to work on, while here we don't give you kind of a project to work on for code, we do give you the main engine, all right? And the main engine is this, okay? Is this simulate function. So use this code, copy it into your project, modifies it as you would like. This is what we're suggesting as a basis for your discrete event simulation engine. Okay. All right. Just to be clear. Okay, then you get to task 4. And in task 4, what you want to do is you want to run simnet estimation on the 3 test cases, on the always slow, the always fast, and the super fast modulation. So these are the test cases you had in task 2. And you want to show that the result that you have, the estimation result, is close to the theoretical result that you would have computed here. Okay, again, we have theoretical results for the non-modulated case. If that doesn't work, then something's broken, all right? And if it works, well, it doesn't mean that the modulation is done properly, but probably if you did a bit more code review and looking at the trace here, etc., the modulation might be good as well. And then finally, you get to task 5, which is to use your code for analyzing something that's not really known. I mean, if it's interesting, it can even be a basis for a start if there's then some theory, a research paper in the field of applied probability, stochastic modeling, Qs and stuff like that. But this is, of course, just a project just to kind of get, just to do something. Well, what we're asking you to do here is to see what does modulation do on the mean Q sizes. Okay, so what we would want to see is we would want to see 4 plots, one for each scenario. And in each scenario, we'd want to see multiple curves, one curve for each value of R. So, for example, if it's at 0.5, it means half the time we're modulated, half the time we're not. Sorry. Half the time we're in slow, half the time we're in fast, half the time we're slow, half the time we're fast. Okay, now 0.9 is mostly in fast. 0.1 is mostly in slow. Okay, but the way you do this with the set scenario function is still rho star is going to be fixed with the rho star. So what I want to say is you've got here now, this is going to be rho star. Okay, and you might have like a curve like this for 0.1. And then maybe for 0.5, I'll just pick a different one. You might have, I don't know, that's what we do in the simulation, a different curve that's a bit higher. Okay, so have a legend like this, and have 4 plots like this, one for each scenario. That's it. That's all you need to do. You're just asked to comment on this if you get some insight from this result. It's actually not exactly clear what we're going to get, but it's well specified. All right, so good luck with this project. I know that this description might seem long, but this project is much easier than project 1 in many ways, and also because of the fact you're much more proficient. So good luck and enjoy. Bye.